Welcome back to week 2 of the Containment Seal mini-series. This week we review the different designs of containment seals available on the market. As we mentioned in the previous video, containment seals can be contacting or non-contacting designs. AESSEAL and indeed most major seal companies offer both types. Quite often, contacting containment seals use a special self-lubricating, dry-running carbon with narrow face width and light spring load for low heat generation in operation. This prevents rapid wear. Don't forget these designs need to last for 25,000 running hours as per the API 682 standard. The non-contacting containment seal uses face modifying features to cause lift and a separation gap when running, often referred to in the API standard as hydrodynamic features, which can be seen etched into the faces on screen. The contacting type will generate heat and will wear out over time, hopefully not before 25,000 hours of operation. The design should have very low levels of leakage in both normal dry running and when the primary seal has failed and the containment seal is containing a wet process fluid. The non-contacting type, by contrast, has in theory no seal face wear or heat generation. However, in normal operation and under primary seal face failure conditions, the leakage will be commensurately higher than in contacting designs. The grooves in the face can also clog with primary seal leakage and debris, especially on Plan 75 applications, if not supported correctly with a Plan 72. The key to selecting containment seal piping plans is understanding if the process fluid is vaporizing at ambient conditions. Vaporizing fluids will use Plan 76 with the recommended Plan 72. Condensing fluids will use a Plan 75 with 72. It is most probable that this will be a C5 hydrocarbon or heavier depending on the minimum ambient temperature and the flare back pressure. Therefore, we consider mixed phase. For example, an overhead reflux pump will always have some small percentage of heavier liquids which will condense. One thing often ignored is the summer and winter ambient temperatures. Some leakage could exhibit as a vapour in the summer months, but formulate a liquid in the colder winter months. The key to selection is really understanding the process and how it behaves. This leakage chart is actually published in API 682 4th edition and was first published by a major competitor to AESSEAL in 2002. Please note that the x-axis is logarithmic scale, so the differences in the bar charts are significant. Condensing liquid leakage would occur in the event of a primary seal failure, and the graph displays the level of leakage from the containment seal based on a 50mm shaft at 2.75 bar, 40 psi. Leakage from non-contacting seals are a significant order of magnitude higher than contacting seals, as it's due to the fact that the grooves in the seal faces physically pump liquid across the face. When you consider the maximum allowable liquid leakage from a fully qualified API 682 single seal of 5.6 grams per hour, the non-contacting seal leakage of 45 cubic centimetres per minute is nearly 480 times the allowable normal leakage. If we consider the 8-hour maximum running period in API 682, this equates to a total of 21.6 litres of leakage, or 4.5 gallons. If we look at the same chart again, but for emissions rather than liquid leakage, and in this case propane for the same seal design, but this time at 0.7 bar or approximately 10 psi. This is generally the alarm pressure of the containment seal interspace. Emissions from non-contacting seals are an order of magnitude of 15 times higher than contacting seals, by virtue of the fact that there is face separation in normal operation. If not using a Plan 72 sweep on these seal designs, this equates to just over 14 normalised litres of leakage of propane over an 8-hour period. According to API 682, clause 10.3.2.3.2, the vapour leakage maximum limit is 1,000 millilitres per cubic metre, or 1,000 parts per million volume at any point in time. It often becomes difficult to benchmark the limit to a total leakage rate over time, so this does become a little subjective in terms of a direct comparison. Tune in next week for the next session where we consider whether a containment seal is actually a true dual seal.